Hey guys, what's up? This is my first video on mathematical studies. So, yeah, let's get started. In ancient times, there was a problem that was considered very difficult or almost impossible by some mathematicians. But as you have heard of the name of Euler, the greatest mathematician of all time, he basically cracked this problem, and this problem is the infamous Basel problem. You can see this here in this part: 1 plus 1 upon 4 plus 1 upon 9 plus dot 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 up to 1 upon 100. These are basically sigma of 1 upon n square, where n takes the value of 1 up to infinity. And this is Euler's proof. This is what I was talking about, this thing. And even I don't understand the full logic behind it, because I'm no mathematician either. So I'm gonna start reading with you guys and understanding along the way, because mathematics is not just memorizing steps. It is very different from other subjects, as it realizes you to understand what is saying. So let's get started. Starts with an nth degree of infinite polynomial px with non-zero roots, this where px is equals to 0. So what Euler did was assume a function px is equals to 1 minus x upon a1. You can assume that, okay. When you substitute x is equals to 0 in the factored form of the polynomial, what you get 1, obviously, because x upon a becomes 0 as x is equal to 0, and all of those terms, and p0 would be 1. Okay, Euler's next claim is what holds for a finite polynomial holds for an infinite polynomial. This statement here it holds, but I don't understand on what grounds Euler is saying this. But let's move on. Like, for example, in this px is equals to 1 minus x square upon 3 factorial. I'm assuming you guys know what factorial is, but x square upon 5 factorial minus x power 6 upon 7 factorial. This would be, if for x is equals to p0 would be 1 here also. And second, Euler needed to use the series expansion of sin x, which looks like this. Yeah, this is a very famous and now common expansion of sin x. If you like take x common and substitute x under sin x, that would be sin x upon x is equals to 1 minus x square upon 3 factorial plus x power 4 upon 5 factorial minus x power 6 upon 7 factorial, and so on. And when you put limit x tends to 0, the whole thing becomes 1. And this is also an identity in limits chapter that you have studied. Yeah, and for the Euler's proof, Euler used the information from above to start the proof. Okay, px is equals to 1 minus x square upon 3 factorial. He is using this a polynomial. On what grounds, it's not known here, and it's just that he got it out of thin air, but that's not the case. Okay, but let's move it. By looking at this formula, we clearly, obviously p0 is equals to 1, as we further established. Dividing and multiplying by x, as this does not change the function in any way, shape or form, but it makes the function sin x upon x, what I was talking earlier, that this function becomes the same as sin x, function sin x upon x. And when p0 is equals to, here would be equal to 1, and this is where we get the limit formula. And further on, he has multiplied x upon x to get this series equivalent to sin x upon x. The equation of above has zeros at x is equals to plus minus k. Yeah, and this is from the chapter of trigonometric equations. if you don't understand this, you need to watch those and understand the concept there. And yeah, and we come again of this 1 minus x square upon 3 factorial plus x power 4 upon 5 factorial minus x power 6 upon 7 factorial. This is px. Okay, and what Euler did is remarkably simple, as the 1 minus x upon pi, 1 minus x upon minus pi. And where is he getting this? He is getting this from the as the equation has zeros at x is equals to plus minus k pi, where k is every positive integer, as but x will have all the real values of pi with an integer. So and if if you take x k for 1, then x would be plus minus pi. If x would be pi, like plus pi, then this first term would be 0. And if x would be minus and then x would be pi here in the second term, and that will be minus pi minus 1, that would be 2, but the whole series would be 0. And if x is equals to minus pi, then this the first term would be 2, but the second term would be 0. So what this is showing, that these are the zeros of the polynomial, isn't it? So let's move on. And Euler proved that this is the identity, a minus b bracket a plus b, if you multiply that, it would be a square minus b square. It's a very basic identity. Now what Euler did was, now Euler expanded the infinite product equation above to get this. What he basically did was he expanded the infinite product equation, and he arrived at this. Okay, now px is equals to 1 minus 1 upon pi square plus 1 upon 4 pi square plus 1 upon 9 pi square plus 16 for if we take x square common in this one, 1 minus x square upon pi square, this equation. Yes, now the what we have taken as px is equals to 1 minus x square upon 3 factorial from above. Now what he did he took the coefficients from 1 minus x square upon 3 factorial plus this px and set them equal to the equation above. This, yes, just wait a second. Yes, this the term in front of the x square coefficient, this is the coefficient, and in px the above equation is 1 minus 1 upon 3 factorial x square. So these both equations are equal, so 1 upon 3 minus 1 upon 3 factorial would be equal to minus 1 upon pi square plus 1 upon 4 pi square, because the coefficients are same. And 1 upon 3 factorial is 6. This is just basic thing, and the minus sign will get cancelled out, and so I'm sorry. And what will happen is this this term series we could get 1 plus 1 upon 4 plus 1 upon 9 plus 16. This is the original series that we needed to prove. And if we send x square to the other side, it would get pi square upon 6. That is how we get this series. The points to note about this is that this is an original proof by Euler, and this is also a very fantastic proof on how different series could help you understand very different concept. For example, this equation that we were initially we have to find out, uh, nobody could think about it that we would be getting this answer in sine x series, isn't it? And till here this is very simple, but 1 minus x upon pi, 1 minus x upon minus pi, substituting all the zeros of the equation, this is also very crucial. For example, most people, what would they would do, they would write x minus pi, bracket x minus pi as being the roots, but Euler did it in this format for it to be applied correctly. And yeah, and when he just what should I say, yeah, when he grouped together the x square terms, and he could have done with the x cube terms, that's not a problem, but we have to, when he sees the series, that in taking pi square common, he would get 1 plus 1 upon 4 plus 1 upon 9 plus 1 upon 16. He would be like, oh yeah, this is a series that I want to find out. And then equating the it's just a matter of equating the coefficients again, and then yeah, it's again simple. But it is also shows how nature behaves in by understanding mathematics, because nobody could have thought about that 1 plus 1 upon 4 plus 1 upon 9 plus 1 upon 16, all of these are rational numbers, but the summation of rational numbers up to infinity could be equal to pi square upon 6, an irrational number. That is really mind boggling, and the thing that I love about mathematics. So if you love this video, please like. And second of all, I was also reading this proof with you here right now. I didn't have studied this proof extensively for months, and it's not nothing like that. I am also learning because I am also a student, and yeah, I'm I just like mathematics. I don't want to show the world that, oh, I'm so brilliant and I know these proofs, and no, I just want to make people fascinated with mathematics, that's all. Yeah, so thank you.